Assalamualaikum. Hi, good day. My name is Anuar bin Pawan, student ID 2017463466, currently enrolling for CEEC 950 PhD in Civil Engineering. Today, I would like to update my progress research report throughout my 8th semester. This is the overview of my research progress presentation. Item 1 to 4 is about research candidate and brief information about my research, followed by item 5 about my major milestone on the research, then item 6 about the timeline, item 7 status of publication, item 8 status of thesis writing, and finally the item 9 planning for next semester. About student information, my name is Anuar bin Pawan. Student ID 2017463466, enrolling for PhD in Civil Engineering since September 2017. A little bit background information about myself. I was working as mechanical engineer in Department of Railways from 2005 to 2009. This department is under Ministry of Transport. Then in September 2009 until October 2010, I pursued my master degree in railway engineering in Birmingham University. Once completed my master degree, I returned to public work department as a senior mechanical engineer, posting in land transport division under Ministry of Work. The work and the role and responsibility much more on overviewing the railway project in public works department. My research main supervisor is engineer technologist Dr. Anizahayati binti Ali Sibra Molisi, senior lecturer in faculty of civil engineering, supported with two co-supervisors, Professor Madya Technologist Dr. Zuraida binti Saleh from Faculty of Mechanical Engineering, and Technologist Dr. Hajjah Noliyati binti Muhammad Amin, Senior Lecturer in Faculty of Civil Engineering, UITM Shah Alam. My research title is Prediction Model Using Fatigue Strength Analysis of Reclaimed Steel Rail Jointing System. The title has 5 underlined words, which is prediction model, defined as a process of using known results to create, process, and validate a model that can be used to forecast future outcomes. Fatigue strength analysis, which is the fatigue limit, is number of cycles of stress of a specific character that a specimen or material can withhold without failure. Reclaim also means a retrieve or recovered material that has been used subject to assessment. In this case, either it is still serviceable or at the end of its service life. A steel rail is a pair of parallel bars made of iron alloy laid on prepared track or roadways, etc. It serves as a guide and running surface for the railway wheels. Jointing system is a splice connecting the adjacent ends of the rail. So in short, the title is about predictive models that analyze past or known performance to assess railway joints exhibit specific behavior to prevent rail breakage in the future. I am now proceed with the introduction to the study. Railway system worldwide has been instrumental in facilitating passenger trips and transporting millions of tons kilometers of cargo. A critical component of this railway system is the steel rail, which plays a vital role in securing transferring vertical loads to the ground while enduring rigorous rail-wheel interactions. In the diagram on the left, you observe that the train with a load of 200 kilonewton or 20-ton axle load transferred to a vertical load of 100 kilonewton at on each wheels. This load is then further transferred to the rail over a small contact patch. This contact patch is about the size of 1 centimeter squared. Consequently, the mean stress experienced by the rail is about 100 kilonewton per centimeter squared, which is equivalent to outstanding pressure of 110,000 bars. The remaining portion of the load is subsequently transferred to the rail pad base plate to the slipper to the ballast bed, and further to the substructures. From its rigorous working conditions, some rails are used until its end of service life. Some are recovered earlier due to line upgrades. For example, in Malaysian Ipoh pada masa single line upgrade, the track is about 330 km. The track has been utilized for operation less than 3 years. There are about 17,000 ton of metals or steel rail worth about 54 million. It's going to be reused for another project. Another project, which is Klang Valley Double track route to KL Station to Klang South, Salak South to Seremban, and Simpang Port to Port Klang, about 260-kilometer double track. It operates in 1995 and being rehabilitated in 2016, only after 22 years of operation. Uh, there is no clear decision either the steel rail are going to be reused or going to be recycled as scrap. So how what are the main decision? Either we can reuse the rail or we should recycle the rails. I am now going to explain about the major research milestone. There are 7 major items in this milestone. The first 3, problem statement, objective, and scope of studies, already agreed upon, and there will be no changes. Item 4 to 7, literature review, is going to be work in progress, ongoing for data analysis to include CDM, continuum damage mechanics, and prediction modeling. The research methodology also being revised, being omitting some area of model analysis, and data collection also being revised to include actual train load data, and data analysis also ongoing for input and revised numerical analysis modeling. Item 6 is about the timeline. Status 7 for status of publication. Item 8 status of thesis writing, and item 9 is planning for the next semester. The issues that initiate this research is the use of reclaimed rails in railway track material. Either the rail are still serviceable or not. The issues of reclaimed rails become a problem when these rails are discarded, perceived as a high risk due to its unknown conditions and low safety performance. It has been discarded as a recycled scrap material. However, these reclaimed rails in Switzerland has been reused more than 30% of its track materials after thorough assessment as it is serviceable. In Malaysia case, before our project for Ipoh Padang Besar begins, Ministry of Transport already donated us our rails for Singapore Kunming lines. Um, in regards to the welded joint in reclaimed rails, it has been a practice to cut and replace with a new weld. It is considered a wastage of 2 to 5% material, and then it's require additional welding process to rejoin the cut rail. So there are escalates problem statement around the industry that rail well or rail joints defect are main contributor to the rail accidents. Secondly, the welded rail defects are difficult to identify. Thirdly, there will be abundance of rail. Temporary has been used in short term and due to line upgrades, and there are also a problem with the track maintenance. It is a problem for the industry to determine the rail defects as in the weld joints. Liu, in his study about U.S. trail derailment in United States from 2000 to 2010, has come out with this statistical data where broken rail or well occurred 13 numbers of 50% more than average of 8.6. In terms of how frequent their occurrences, the broken rail and other rail defects recorded almost 9 times higher than the average of 89 numbers. Based on this statistically data, the broken rails or well dominate both severity and frequency of the rail accidents. Welded rail defects are also difficult to identify. The industries has agreed that crack growth in the web and crack initiated in the head are very difficult to identify, and it is require several transducers on different angles to identify its presence. This is a very slow process and require highly skilled workers. If the cracks are not being identified or the weld are not removed from the surface, the internal crack region will propagate and further extended until uncontrollable size, and this is at the end will cause the rail to break. There is also a problem with the number of rails has been used and retired earlier than is intended design life. For example, earlier railways in 19th centuries and 20th centuries in the most of part of the world, the axle load for the train is about 10 to 20 ton per axle load. Only after 2010, most of the region has increased their loading capacity to maximum of now in United States about 42.5 ton per axle loads. Therefore, those railways are still in the service but unable to cater for higher carrying capacity will be removed from the line and will be will be part of the wastage if it is not treated as part of the serviceable rail. To identify defects in welded rail also requires a major undertaking and commitment and becomes a track maintenance issues for many railway operations. It requires full range of skilled workers, fully functional machine and high capacity machines. Even the adequate stock and forecasting for reordering will take time. In terms of operation, the rail need to be resurfaced or regrinding to minimize the formation of surface crack. And this is very important to remove the surface crack from its critical size. For internal crack inspection also requires ultrasonic inspection as mentioned earlier, where it requires 70 degrees transducers, 40%, 40 degrees and 0 degrees transducers. These transducers will inspect and provide assessment report of the condition. But at this moment, the current high performance machine also operates at 30 to 70 kilometer per hours, and with passenger train running at 120 kilometer per hour, this inspection train will be delayed and mostly will be operation during the night time. Therefore, it is very important to have a supporting tools to predict rail performance based on predetermined fatigue life or service load conditions to ensure the safe train operation. This studies has five major objectives. First one, to analyze the fatigue stress of steel rail joint, and then to determine the fatigue life of reclaimed steel rail joints, and then uh, the research should be able to establish the relationship between fatigue life at rail joint, basically to compare between the base parent material and then to establish the prediction model based on performance of residual strength. And finally, to establish the fracture control plan using numerical analysis of reclaimed rail joint to determine or to deter rail joint breakage from occurrences. For the scope of study, the first step is to perform the experimental investigation on welded joint. This is to determine the mechanical properties by analyzing the chemical analysis and surface analysis, either the right composition are in place and for the material. And then the author going to perform the mechanical testing performance on the bending test and fatigue life cycle performance on the parent rail and the welded rail. Secondly, second scope is to analyze the crack initiation and propagation using scanning electron microscopy. And then the study will assess the welded joint strength based on microscopic analysis and empirical formula for trend in fatigue failure. The fourth scope is to develop numerical modeling of residual strength and further validate with experimental data. The final scope of study is to establish fracture control plan for rail operation throughout the rail's life cycle, aiming to minimize weld failure. This forecast will utilize the actual train load data from dynamic trains loading obtained from various sites. However, the study faces certain limitations. Firstly, the research has restricted numbers of samples, emphasizing the need for precise and accurately abstract specimen to ensure consistency and repeatability of the experiment. Secondly, there is a scarcity of laboratories that capable of conducting the required EN 14587 tests. In most cases, the service charges of these tests are relatively expensive due to the extended duration and monitoring requirement. One sample for 5 million cycles will take around 1 month, and this is quite a time-consuming process. On the literature review, there are many references in relation to the defects of welded rail and surface crack initiation. Farhanghi and Monsalvides 2007 concluded, even though flush butt weld is superior in quality compared to aluminothermal welding, the flush butt weld still having failure issue due to horizontal split web. According to Sana and Larso, even though the flush butt weld failure is low at 7.9%, most studies found delaying surface crack removal will cause the crack to propagate and continue to cause the rail break. Ekberg and Kabu in experimental review observed subsurface initiated rolling contact of high dynamic contact forces, pressures, and material defect both in wheels and rails often happens in weld. The slow growing defect, however, occur at the foot and web of the rail. Popovic et al. 2014 emphasized on the trend in uncontrolled rail defect, which can threaten the traffic dense safety, increases rail maintenance, and lead to premature removal of rail, or can cause the complete rail failure. Veskovic 2012 outlined surface crack happen during rolling contact fatigue and plastic flow due to high stress at small surface area, which is contact patch. Furthermore, operation-induced factors such as train speed, axle load, traffic density, and maintenance regime plays important role to the propagation of cracks. According to Jedefroida 2014, cracks in weld nucleated in weld bed, specifically at rail web, then grow to critical size. Continuous load at this stage will promote existing crack to grow unstably, which lead to the rail break. There are also supporting literature about reuse of reclaimed rails. Uh, Bricker, Brickerhoff 2012 um, stated that reclaimed rails can be used as relay rail inserts and closures. ARIMA, the American Railway Engineering and Maintenance of Way Association, in their track manual 2006, emphasized that reuse of a rail must follow its rail standards. The rail dismantled from track must be used in accordance to its previous function. For example, the straight track must be used at the straight track, curve at the higher side or low side must be used similar location. Rail Council in 2010, in their study, observation concluded that reuse of serviceable track and signaling components is not a common practice in British Rail. There are also opportunity to refurbish railway infrastructure components as part of a sustainable approach. The author has extended additional literature on prediction technique with MA minor to 1949 analysis shall not lack of dependence from the loading and specimen geometry. Fatigue life determined only by stress strength criterion. GIU et al. 2010 and Suresh 1991 um, use the rules of linear cumulative damage for pump grain and miners, but then it must be included with quantum damage mechanics, where all the fatigue life are predicted using damage parameter cycle by cycle, and continuum damage mechanics include the accumulative or damages from very beginning until the end, which is value added to the linear cumulative damage. In Bhattacharya et al. 1999 agrees to the continuum damage mechanics because damage initiation and accumulation in material are important to be part of the damage formulation before detectable defects happens at microstructure level. CDM includes damage initiation and accumulation in material prior to the formation of detectable defects. SS Kulkarni 2006 um, also recommends periodical in situ measurement to calculate the macro crack initiation propagation. So that from these literatures, it is important to include continuum damage mechanics as a part of accumulation and also non-linear analysis compared to linear cumulative damage as suggested earlier. As for prediction technique, T. Delbert 2003 suggested to include multi-axial loading, tensile and bending. S9 1985 also from his experimental observation review found that the rail head experiences lateral and vertical deflection during rotation due to loads from passing train. Uh, Yu Zebs et al. 2009 outlined three different forces acting on the rail: longitudinal, vertical, and lateral, with bending moment due to lateral force. Maximum happen at the midway of slipper distance. The following is the conceptual framework of this research. First, the input is taken from the experimental data acquisition based on mechanical properties of welded joint to include all the bending, strength, and fatigue stress. And then second input is from the numerical analysis. The process of validation is done through comparing both results for optimized result or error. And this is the output of the optimized model when the experimental data is almost the same or ideally the same with numerical model. Once the input is agreed on, then the model will be loaded with the new operational train data as a actual load And then the author going to put further forecast for the next 10 to 15 years operation. This is part of the continuum damage mechanics um, solver using in the software, so that the final element analysis is going to consider damage accumulation. Then this output going to be part of the fracture control plan. Either the rail well going to withstand the load, or will be fail prematurely upon installation, or maybe in the shorter lifespan compared to the initial service location. As for the flowchart, we have two sections of the process. On the left is experimental, where the author going to conduct the slow bend test, fatigue test, tensile test, hardness, chemical, micro and macro analysis. And then on the right side is the numerical analysis using the finite element models, determine the boundary conditions and the loading that similar to the experiment. Once the error is reduced, or error already optimized, the author going to put the forecast of the train loading as part of the control fracture plan. The methodology involves four major tasks. First, the author going to refer to the existing document and work reference. Second, to perform the experimental works, involve the laboratory works in mechanical to determine mechanical properties and mechanical performance of the welded rails. There will be also additional tasks to acquire in situ data acquisition for the loading of passing trains. And then there will be modeling using finite element software, and then to develop a predictive model and fracture control plan. For the task number one, document and reference study, the author going to review previous studies and gap analysis uh, to perform the pilot test on slow bending test in order to determine the suitable machineries available to perform the test, and then to model the initial finite element and finite element analysis. And then the author going to analyze the welding process at site. In this case, there is a mentakap and kemayan yard for flush butt welding, and mentakap gemas mentakap site installation. Thirdly, the author going to review the recovered material usage history. There is a records on how long the rail, how many train has been used, the track, etc. Uh, Task number two is to perform the laboratory works, uh, mechanical properties of the welded rails. There is a bending test, 3-point bending will be performed at Heavy Structure Lab, Faculty of Civil Engineering. And then there is also rail weld fatigue test. And then we are going to perform the hardness test at Faculty of Mechanical Engineering. Macro and microstructure test, a check also will be done at Faculty of Mechanical Engineering. Chemical composition are going to do shared either at the Faculty of Chemical Engineering or UniKL. So we have some collaboration with UniKL where we share some samples, and we use their analysis for this purpose. Number 6 is a tensile pull test. This is done to verify the ultimate tensile strength. Thirdly, you're also going to convert all those data from the actual real profile into numerical analysis model, and then going to validate against the experimental data, and then further calibrate to ensure the error is minimized. Finally, task number 4, the author going to come up with the predictive models and control plan to include load from actual rain passing the track, and then to compare with the actual train schedule for the operations. In terms of Gantt chart, um, this is originally when I started the study in September 2017, which is already superseded, and then been revised in March 2022, also being superseded. This is the revised. This is the revised Gantt chart in July 2023. Currently, I have three main tasks, which is literature review, data interpretation, and thesis writing ongoing. Status of publication, there are already three publications, two on proceeding, one on journal, and currently I'm still drafting on numerical modeling of welded joint under fatigue loads. Status of thesis writing now in part 8, semester 8. Chapter 1, introduction, already completed. Chapter 2, literature review. There is a revision on prediction technique. So it comes to 92%. Methodology is about 90% because there is a revision on prediction modeling scenarios. Chapter 4, result and discussion, is about 78%. Adding prediction modeling using actual train as a data input for both passenger and freight trains. And finally, the chapter 5 for conclusion is about 60%. I am planning for the next semester to complete chapter 2 and 3, and result and discussion will be uh, for the for the improve towards 90 and 95% respectively. With that last slide, I am now concluding my progress report update. Thank you. Assalamualaikum.